Let's dive into the world of processes, the fundamental units of execution in an operating system. A process is an active program in execution, transitioning from a passive executable file on disk to an active entity in memory. Processes can start through various methods like g-clicks or command line entries, and a single program can spawn multiple processes. As a process executes, it changes states: new, running, waiting, ready, and terminated. Each state represents a different phase in the process life cycle, from creation to completion. The process control block is a data structure that holds all the information about a process, including its state, program counter, CPU registers, scheduling information, memory management, accounting, and I/O status. Threads are the smallest units of processing within an operating system. Modern systems allow multiple threads within a single process, enabling concurrent execution. Process scheduling is crucial for managing the execution of processes. It involves removing processes from the CPU and selecting others based on a specific strategy, ensuring efficient multitasking. Process scheduling involves different queues like job, ready, and device queues. These queues help manage processes at various stages, optimizing CPU usage and process execution. There are three main types of process schedulers: short-term, long-term, and medium-term. Each plays a distinct role in managing process execution and system performance. The short-term scheduler, or CPU scheduler, selects which process to execute next. It operates frequently and must be fast to ensure smooth system performance. The long-term scheduler, or job scheduler, manages which processes enter the ready queue, while the medium-term scheduler handles swapping processes in and out of memory. Operating systems provide mechanisms for process creation and termination. Processes can create child processes, forming a hierarchy, and are managed using process identifiers. Processes can be created using system calls like fork. The parent process creates a child process, which can further create its own processes, forming a tree structure. In Unix, the fork system call creates a new process, and exec replaces the process's memory space with a new program, allowing dynamic process management. When a process completes its execution, it terminates using the exit system call, returning status data to its parent. Resources are deallocated, and child processes can be terminated using abort if needed. In some systems, if a parent process terminates, all its child processes must also terminate, known as cascading termination. This ensures no orphan processes remain. Inter-process communication allows processes to communicate and synchronize their actions. It can occur between related or unrelated processes, facilitating coordination. There are two primary models of IPC: message passing and shared memory. Each model provides different mechanisms for process communication. Shared memory allows processes to communicate by accessing a common memory area. Synchronization mechanisms are essential to manage access and ensure data consistency. Message passing enables processes to communicate without shared variables. Processes send and receive messages, with IPC facilities providing operations for message exchange. To implement message passing, processes establish a communication link and exchange messages. This can be done through physical or logical links, with options for direct or indirect communication. In direct communication, processes explicitly name each other to send and receive messages. Links are established automatically, and each pair of processes has a unique communication link. Messages in indirect communication are directed and received from mailboxes. Each mailbox has a unique ID, and processes can only communicate if they share a mailbox. The link is established only if processes share a common mailbox, and each pair of processes may share several communication links. The link can be unidirectional or bidirectional. The queue of messages attached to the link can be implemented in three ways: zero capacity, where no messages are queued and the sender must wait for the receiver; bounded capacity, where the sender must wait if the link is full; and unbounded capacity, where the sender never waits. Sockets facilitate communication between two processes on the same or different machines. They are used in a client-server framework and consist of the IP address and port number. Socket communication is low-level as sockets only transfer an unstructured byte stream across processes. A socket is an endpoint for communication, defined by the concatenation of an IP address and port number. For example, the socket 161.25.19.8/1625 refers to port 1625 on host 161.25.19.8. Communication consists of a pair of sockets. Ports below 1024 are well known and used for standard services. The special IP address 127.0.0.1, or loopback, refers to the system on which the process is running. Pipes act as a conduit allowing two processes to communicate. There are two types of pipes: ordinary pipes and named pipes. For two-way communication, two pipes are required. Ordinary pipes cannot be accessed from outside the process that created them, typically used by a parent process to communicate with a child process. Named pipes can be accessed without a parent-child relationship. Ordinary pipes allow communication in a standard producer-consumer style. The producer writes to one end, the write end, and the consumer reads from the other end, the read end. Ordinary pipes are unidirectional and require a parent-child relationship between communicating processes.